So good morning, everyone, and welcome to my own part of CMCHM 101. My name is Dr. Ejia, and I want to presume I'm the third lecturer. So I will be taking you the next part for CMCHM 101, and I've already told you my name. And please encourage your classmates to join the lecture, because this lecture is just for 1 hour and we don't have enough time. So I'll just go ahead and share my slide. So for my own course content, I will be looking at electronic configuration. Then we'll also look at periodicity and building up of the periodic table. That is for the periodic table and the electronic configuration. And after that, we are going to look at radioactivity. We also look at chemical equations and chemical reactions and stoichiometry. I'm not speaking. When I speak, you will hear. I'm trying to adjust some things. So on the electronic configuration, we are going to learn how to write the electronic configuration of elements on the periodic table. So I encourage you to learn the electronic configuration at least for the first 30 elements. Then we are also going to look at how to justify the trends of atomic radial ionization energies, electronegativity of the element. Please, can you hear me? Because I'm having echo. It's echoing here. Can you hear me? Okay, thank you. Okay, thank you. I want to start again. I was having some echoes, so I'm starting all over again. So as I said, we are going to start with the course content, electronic configuration, periodicity and build-up of the periodic table. We look at radioactivity, chemical equations, chemical reactions, and stoichiometry. So for the electronic configuration, you have to know how to write the electronic configuration of elements on the periodic table. And as I said earlier, at least the first 30 elements. Then we'll also justify the trends of atomic radial ionization energies, electronegativity of the element based on their position in the periodic table. So for the electronic configuration, so as I said, we are going to start with electronic configurations. So electronic configuration basically refers to the arrangement of electrons in the atomic orbitals. That is the way that the elements are arranged in the periodic table according to their atomic number. Also, from electronic configuration, we'll be able to know the distribution of electrons among the different energy levels and the subshells. You can't hear me and you can't see my screen. Why? Some people say they can hear. So why can't you hear? You that cannot hear, what is the problem? It's not my fault. Okay, we can. They say they can hear me. So please check your system. It should be from your system. Please do check your system because others can hear me very well. So please do check your system. So as I said, we are on electronic configuration. So if we look, for example, if we look at lithium, the atomic number is 3. So for the electronic configuration, we normally say 1s. This 1 and 2 is the first shell. 2 is telling us is the second shell. Of course, you know we have 1s, 2s, 2p, 3s. So those are actually telling us the shell and their number. And the subscript is actually telling us the number of electrons. So this electronic configuration tells us that lithium has, as I said, the atomic number is 3, and it has 2 electrons in the first shell, and it has 1 electron in the other sub shell. So if you're able to understand the electronic configuration, then we'll be able to determine some chemical and physical properties of this element, because the electronic configuration will always tell us the number of electrons in the shell, and also the valence electron, which plays a very significant role in the chemical and the physical properties. So now, how do we write electronic configuration? Having known what electronic configuration is, how do we write electronic configurations? Of course, for us to write the electronic configuration, we have to use some symbols. Symbols like your S, which will tell us the number, the shell, and also the subscript, which will tell us the number of electrons in that subshell. So let's look at how to write some electronic configurations. So I will let's use the blackboard so that we can. Okay. So let's start from the first one. Of course, the first atom or element is hydrogen. Of course, hydrogen, the atomic number is 1. So if you want to write the electronic configuration, we normally say 1s1. Of course, 1 is the number of shell, the shell number, that is N, and S is the shell, and the 1 here is the subscript. If you look at helium, the atomic number is what? 3. So if we want to write the electronic configuration, we'll say 1s2, because for the orbitals, we have the s orbital, we have the p orbital, we have the d orbital, and we have the f orbital. And the maximum electron for each orbital for your s is 2. For your p orbital, it can contain a maximum of 6. For your d orbital, it can contain a maximum of 10. And for your f orbital, it can contain a maximum of 14 electrons. So what this means that this orbital is completely filled in a helium. So for your lithium, so this is 2. So for your lithium, which has atomic number of 3, so we are now going to write 1s2 as helium completely filled 2s1, because this is telling us that is the essence of this parenthesis. So the next one is beryllium. Your beryllium, of course, the atomic number is 4. So you can write 1s2, 2s2. Alternatively, you can write helium 2s2. So the last one is our boron. Our boron is 5. Boron atomic number is 5. So it's going to be 1s2, 2s2. So the next orbital is going to be p, and we have 2p, we have 3p, we have 4p, we have 5p. So the next one is going to be 2p1. So you can also write it as helium. Helium what? 2s2, 2p1. And as I said, the maximum number of your p orbital, the maximum number of electron is 6. The next one is carbon. Our carbon has the atomic number of 6. Our carbon is 6. So we can write what? 1s2, 2s2, 2p2. Or we can write helium what? 2s2, 2p2. So can we write for nitrogen? Can we write the electronic configuration for nitrogen? Nitrogen is how many? 7. That is the atomic number. So can we put that in the chart? I'm going to the chart to check. Can you write the electronic configuration for your nitrogen? I'm checking the chart. Okay, 1s2, 2s2, 2p3, or we can write helium. Okay, correct. Thank you very much. Write it using helium. So it can be helium what? 2s2, 2p3, 2s2, 2p. Thank you very much. So I can see that we are following. Good. So we can continue until we get to neon. We get to neon. Neon is going to be what? 1s2, 2s2, 2p6. That is your neon. So after neon, the next one is what? Sodium. Our sodium is what? 11, because our neon is 10. So your sodium, you can write 1s2, 2s2, 2p6. After 2p, what is the next one? That is our 3s. So we have 3s1. Or alternatively, you can write neon, because it's completely filled, 3s1. The next one is your what? Magnesium. Magnesium is 12. So we can write it, instead of writing 1s2, 2s2, 2p, we can just write neon 3s2. Are we together? Are we together? Till we get to what? We get to potassium. No, we get to argon. That is where we have another. Argon is your what? Argon is 18. So you continue from magnesium until you get to argon. Argon is 18. And our argon is what? 1s2, 2s2, 2p6, 3s2, 3p6. That is our argon. So after argon, the next one is what? Potassium, which is 19. So our potassium, instead of writing all these, after 3p6, the next one is going to be what? 4s1. So we can just write argon. We can just write argon. After argon, the next one is your calcium. Your calcium is 20. So we can just write. This is basically how to write your electronic configuration. So as I said, at least you should be able to write for the first 30 elements. That is the first 30 elements. So from your argon, we now get to what? From our calcium, which is 20. The next one, we are now entering the transition element. You have your scandium. Scandium is 20 because your potassium is 19. So your scandium, you can now write argon 4s2. After your 4s, the next one is your 3d1. Mind you, your potassium, which is 19, is what? Argon 4s1. So your scandium is 20. So you have your argon 4s to 3d1. Sometimes you can see it in a textbook as written as argon. That is from argon, because we are now entering the d orbitals. 3d1, 4s2. Either of them is correct, because the energy between your 4s and your 3d is very close. So either of them can come first. So most times, this is the way it is written in the textbook, 3d1, 4s2, because from your scandium, these are now your transition elements. So the d orbital sometimes supersedes the s orbital. So you keep on writing. After scandium, the next one, you continue until you get to zinc. Your zinc is going to be argon 3d10, 4s2. So this is actually how to write your electronic configuration. So you know where to use helium. So you know where to use helium. You know where to use neon. And you know where to use your argon. Wherever you have the orbitals completely filled, the next electronic configuration should have the completely filled there. Parenthesis. I hope you can still hear me. I can see people raising their hands. Okay, thank you very much. Okay, so that is how to write electronic configuration. So these are, I have all of them here, but we're not going to go through that again. So now, having learned how to write electronic configuration, this is actually what I've already explained. Instead of writing your 1s1, 1s2, 2s2, 2p6, you can actually know the ground state electronic configuration of each of these elements. Like this is your group 1, group 2, group 3, group 4, group 5, group 6. Let me put it in slideshow. Okay. So this is your group 1, group 2, group 3, 8. So N here represents the number of shell, while S is the orbital, and the subscript is the number of electron in that subshell. So this is 1s. So this is, you expect this to be your 2s. So as you go on, you start increasing the number of you see that the number of electrons is actually increasing. Sorry. So this is also for the transition element. This is your scandium up to your zinc. So you have your D1, D5, and D10. What this actually means that for each of these, like for your D1 and your D10, well, as we go on, we are going to see that these elements here are very, very stable when they have either 5 electrons in the d orbital or 10 electrons in the d orbital. So this is a short form of writing your electronic configuration in the ground state. So I want to know the NS and the NP. You'll be able to know what the number of shell and the valence electron. So this is telling us that this has 1 valence electron. The second has this second group has 3, 4, 5, 3, 4 fluorescence. And for this, you see that for your P, that is for your nitrogen and your neon. We are going to see all these as we go through the lecture. So now let's look at periodic table, periodicity, and the building up of your periodic table. Now, what is your periodic table? When we talk about periodic table, from the word table, we know that it's a table. It's a tabular arrangement of elements in the order of increasing atomic number. When we talk about atomic number, we are actually looking at the number of protons. And because of this arrangement in order of increasing atomic number, most times we normally have this element having similar properties at regular intervals because the atomic number increases by 1. So you see that most times you have their physical and chemical properties are actually similar. So what is actually what we call periodicity? That is the recurring trend. When there's a recurring trend in the physical or the chemical properties, that is actually what is referred to as periodicity. So periodicity refers to the recurring trends that are observed in properties of elements in the periodic table. And because of this periodicity, we'll be able to have variations, especially in terms of the atomic structure and also some physical properties. Now, as I said, because of the periodicity, because there's a recurring trend, we normally have some periodic properties that we are going to actually consider. As I said, these periodic properties actually depend on the electronic configuration. So for you to be able to explain periodic properties very well, you must know how to write electronic configuration. Because as I said, from electronic configuration, you'll be able to know the valence electron. And as I said, most times the valence electron actually affect most of these periodic properties, either the physical or the chemical properties. And also, you'll be able to know the size of the shell. If it's the size of the shell is increasing or the size of the shell is the same and the electrons are being added. So electronic configuration is fundamental for you to be able to explain periodic properties. And some of the periodic properties we are going to look at, or that is common in the periodic table, is usually we have the atomic radius, we have the ionic radius, we have ionization energy, we have electron affinity, and we have electronegativity. But for this lecture, we are going to concentrate on just 3: the atomic radius, the ionization energy, and electronegativity. So we are going to start with atomic radius. Aside the atomic radius, ionization energy, and electronegativity, we are also going to justify the trends. It's not enough for us to just know what atomic radius is, ionization energy, and electronegativity. We are also going to justify the trend in the periodic table. And I know even in your maybe in your secondary school, I'm sure you have come across it before, but now we are going to look at deep concept. So as I said, we're also going to justify the trends of atomic radii, ionization energies, electronegativity of elements based on their position in the periodic table. So that is why you need to know your electronic configuration. So we are starting with atomic radii. What is atomic radii, or what we call atomic radius? Atomic radius is defined as half the distance between two nuclei of a homodiatomic molecule. That means for you to be able to get the atomic radius of a particular atom, it has to be 2 of that atom. Let's say your chlorine, between 2 nuclei of a homodiatomic molecule. So between your chlorine, so Cl2, that means you have chlorine. So that is how you'll be able to get the atomic radius. So have that distance between those 2 atoms will give you the atomic radius. Now, what is the trend? We have known what atomic radius is. What is the trend? Across the period and down the group. Because we have elements across, this is your periodic table. We have elements down the group and we have elements across the period. So what is the trend of atomic radius? Now, if you look at this, what I have here, you see that as you go down the group, what happens? The size is increasing because we are increasing the shell from 1s to 2s to 3s to 4s to 5s. So the shell is increasing. So the size is actually increasing. So invariably, the distance between the two nuclei of a homodiatomic molecule is also increasing. The distance between them, because the size is increasing. So what do we say down the group? So atomic radius does what? Increases down the group due to increase in atomic size. Aside increase in atomic size, there's also a decrease in the nuclear pool, because decrease in nuclear pool between the nucleus and the valence electron. So the valence electron is very, very far from the nucleus. So that is why your atomic radius increases. So now what happens across the period? You see that across the period, we have, this is our period 3 element. We have our sodium, magnesium, up to your chlorine. What do we have across the period? Across the period, you see that the shell is reducing. Why is the shell reducing? Because this third shell is actually, all the electrons are being added on the third shell. And so because the electron is being added on the third shell, what happens? The size reduces because the valence electron is actually pulling the electrons together. Unlike here, the valence electron is further away. Here, the valence electron is even increasing because more electrons are being added to the same shell. So the distance between the two nuclei of a homodiatomic molecule is reducing. So atomic radius decreases across a period owing to increase in the positive charge from the nucleus. So down the group decreases, and you should be able to give us the reason. So now, what are the factors that affect us, which I have shown you from here? Down the group, you see that the energy level is increasing. Across the period, the energy level is not increasing. So energy level of the valence electron. The higher the energy level, the farther the distance from the nucleus. Of course, if it's farther, then the atomic radius will do what? We reduce. So the distance from the nucleus is in the order of this energy level. 7 is farther, followed by the 6th energy level. Of course, the first energy level is closer to the nucleus. So the energy level of the valence electron affects the atomic radius. Another factor that affects your atomic radius is the nuclear charge. The nuclear charge is the number of protons in the nucleus. Of course, we know that the higher the nuclear charge, the closer the electrons to the nucleus. Of course, as you are increasing the atomic number, the number of electrons, the number of protons, and the number of electrons is increasing. So the higher the atomic number, the smaller the size, because the number of proton and the number of electron is increasing. So the nuclear charge is increasing. So invariably, it's pulling the valence electrons more, so the size becomes smaller. So another factor is the nuclear charge. As we increase the protons, then the nuclear charge increases. What we call the screening effect. When we talk about shielding, that is, you are shielding the what? The valence electrons. This is the screening of outermost electrons from the nucleus by the inner electrons. That is, the valence electrons is being shielded from the inner or the inner electrons. So what it means is that if the size is large, of course, that means the shielding effect is large. And what happens to the atomic radius? The atomic radius will decrease. So the larger the size, the greater the shielding or the screening effect. So these are the factors that affect atomic radius. You talk about the number of the shell or the energy of the valence electron. We talk about the nuclear charge, and we talk about the shielding or the screening effect. That is the shielding or screening effect by inner electrons. Of course, that has to do with the size of the atom. Ionization energy. So this is the second periodic energy. Ionization energy mole that you require to remove the most loosely bound electron from a gaseous or what we call an isolated gaseous atom to form. Who is raising his or her hand? Please put it on the chat if you can hear me. Because I saw someone raising up his or. If you have questions, just at the end of the lecture, I'm going to take your questions. Please, if you can hear me, put it on the chat. Okay, if you have question, okay, you can hear me. We can hear you. Okay, thank you very much. If it's a question, put it on the chat. If not, we can hear you, well. I think maybe some people's network are bad because people can hear me. Thank you very much. So as I said, ionization energy is defined as the energy in kilojoule per mole that you require to remove the most loosely bound electron. This most loosely bound electron, of course, you agree with me, is the valence electron from an isolated gaseous atom to form a positive gaseous ion. So what it means is that for ionization energy to occur, energy must be supplied, energy must be absorbed. If it's the ground state, then ionization energy cannot take part. Now, we said that if a small amount of energy is supplied to an atom, electrons may be promoted. Let me tell you what I mean by that. What it means is that if you have, let's say this is your 1s, let's say this is your 2s. So what it means for ionization energy to occur, let's say you have one electron here. If you supply energy to this electron can transit or jump from 1s to 2s. If you just apply just small energy. But for ionization energy to occur, you must apply enough energy that will be able to remove this electron completely. Not just going from 1s to 2s, it must be able to remove the electron completely. So what it means is that you must supply the required amount of energy. So we said if a small amount of energy is supplied to an atom, electrons may be promoted to a higher energy level. That is what I just explained to you from 1s to 2s. But the amount of energy supplied is sufficiently large, the electron may be completely removed. That is your ionization energy. Now, for ionization energy, we have what we call first ionization energy, second ionization energy, third ionization energy, fourth, fifth, and so on and so forth. But first, what is first ionization energy? This is the energy, or what we call the minimum energy that you require, also in kilojoule per mole, is just one, an electron or first electron to form a gaseous ion. To occur, this is an atom, it has to be in the gaseous form, not in ground state. As I said, you must apply sufficient energy, not to promote from 1s to 2s. No, we want to remove it completely. So this is an atom in the gaseous form. For the first ionization energy is going to lose the first valence electron, and that is why you have it as this in the gaseous ionic form. So this is telling us that it has lost one electron. When you see a positive sign, that means that atom or that element is now electron deficient. So it has lost one electron. So for this is the first ionization energy. For the second ionization energy, it's actually going to occur from this ionic element. So it's the gaseous ion from the first ionization energy that will undergo further loss to give us the second ionization energy. So this is now more electron deficient. so it has lost one more electron. This is the second ionization energy. For the third ionization energy is actually going to come from the second ionization energy at our ion to give us the third ionization energy, and it can go on and on. Can we write the fourth ionization energy in the chart from the third ionization energy? Now, for the second, third, or fourth ionization energy, you cannot just go from first to fourth or third. It must go sequentially. So what it means, it must lose the first. After losing the first, it will undergo the second. After the second, it will undergo the third, and so on and so forth. So so you cannot just go from one, you just get to fourth. No, it must go through sequential. First ionization energy, the energy is lower, followed by the second, the third, and so on and so forth. So what it means is that the first ionization energy, of course, is the valence electron is further away from the nucleus. So the energy you require to lose that electron is not actually much because it's further. But as you start going to the second and the third ionization energy, you see that the energy that you require will actually be more, because you are not entering the valence, you are not entering into the valence shell. But we are still going to see a trend where we see what we call half-filled and completely filled subshell. There's going to be some disparity as we go on, and I will explain that to you. It means that energy is usually added. You need to add energy for to leave the valence reduces as the size of the atom increases. So it means that as we go to the group, the size of the atom increases. So the energy you need to remove reduce. So we are seeing a trend down the group and across the period. So ionization energy and atomic radius are inversely proportional because atomic radius has to do with the size. So we say ionization energy and atomic radius are so the larger the atom, the larger the atomic energy. So affect ionization energy. The factors that affect the nuclear, the atomic nuclear, or the effect, and the radius. So I'm not going to explain this again. We've already explained it. I will only explain the subshell. What do we mean by subshell? Let's see what we mean by subshell. What do we mean by subshell? I think I've already explained that. For your subshell, let's say for the S, E, D, let's not go to F because we have 3 subshell. For D, we have 5 subshell. So this is your S, this is your P. We have 3 subshell. This for your D, we have 5 subshell. For your S, if it has 1 electron, it's very, it is very, very stable. If your D has 1, 1, 1, 1, 1, it is very, very stable. If your S has 2, complete stability. So when they have field stability, so if your P has 2, 2, 2, very, very stable. The same thing with this. So that is actually what we mean by half-filled and completely filled stability. Okay. So the subshell, that is what I've just explained to you. An electron from a full or half-full subshell requires additional energy to be removed. Why? Because of stability. As I told you, when it's half full or completely full, then the stability is half filled is as stable as completely filled. and harmful orbitals are stable because when they when like has two, your P, if it has one, all what we call half field stability. When it has just one, when it has the 6, then that is the full stability. So this half or full orbitals have higher ionization energy than expected due to what? Reluctance of the element to their stability. So now, what is the trend? So a group, ionization energy decreases because atomic radius increases and the shielding effect increases. So if we look at this first ionization energy, so let's use this to explain ionization energy down the group and across the period. If you see down the group from your lithium to your sodium to your potassium to your rubidium, you see that your lithium ionization energy is increasing, size is increasing, the shielding effect increasing, the attraction between much. But if you now look at this trend, is increasing. But now when you now get to 8, when you now get to nitrogen, it's supposed to increase, but the value is now very, very high. Why? Because of what we call half field stability. Because your nitrogen here, we have the P3 electronic configuration. So you see that your nitrogen here is high, but your oxygen here is low. We expect your oxygen to be higher than your nitrogen because we said that ionization energy increases as you go from left to right. But you see that your nitrogen, of course, we expect it to be high. It's increasing. But when it now got to oxygen, it now reduced. Why? Because let's look at the electronic configuration of your nitrogen and your oxygen. So your nitrogen is going to be, we are going to have half field stability for your nitrogen. That is your P3. 1, 2, 3. This is your half field stability. When you now get to oxygen, oxygen is going to be what? It's going to be P4, if I'm correct. You have 1, 2, 3, 4. So you have nitrogen have a half field stability, is more stable than your oxygen. That is why the ionization energy for your nitrogen will be higher than your oxygen because of the half field stability. So we experience it in nitrogen. We also experience it when we get to neon because of the completely field from your sodium to your phosphorus. You see that your phosphorus, your sulfur is now lower than your phosphorus because of how field stable. Try to write the electronic configuration of your phosphorus and your sulfur. You see that your phosphorus will have nitrogen, and that is why the ionization energy of your phosphorus is higher than that of sulfur. So atoms in the same period have electrons in the same energy level. They have the same shielding. nuclear charge increases from left to right, exception at half and full orbitals. So we just look briefly block. So for your S and your P block, your S block are metals and your P block for your metals. There's something I want to. So what I would just want you to get enough. I don't want to read what I have here. So for your S and the P, the SL element, they are metals, so they have more tendency to lose electrons, while your P orbitals have more tendency to gain electrons. So you see that for your metals, the ionization energy will actually be lower than the P orbital. So it's like going from your left to your right. So from the left, we have more of metals. As you go to the right, you have more of non-metals. So ionization energy of your S and your P block element will actually depend on the type of element. As I said, your S block element are more of your metals, and they have more tendency to lose electron and become stable. So changes in the second, third, fourth, fifth, and sixth row of the S and P block element follow the same pattern. Ionization energies increases from left to right across each row. As I said, you are going from the S orbital to the P orbital due to the valence electrons of the radius down. Now, what I want you to know is the element that form positive ions most easily energies, and that these elements are the hardest to ionize, and also their ionization So sorry. I think I was logged out. And so next on Monday, we'll continue. I know I stopped at ionization energy. So sorry about that. On Monday, we'll continue. I will send you the recorded lecture because I recorded it. So I was logged out. I'm so sorry about that. I tried to log in again. Yeah. Of course, you know that because you people were already 300, I couldn't log in. So I couldn't log in again because the class was already filled up. So I'm so sorry about that. Monday, I believe we'll have a better network. So I'll see you on Monday. So sorry about that.